Welcome to today's webinar, Foundations for Extremes. My name is Luke Carruthers with Civil and Structural Engineer Media. Thank you for joining this webinar, which is sponsored by Chance. Before we begin today's presentation, first some general information about the webinar and the GoToWebinar platform. The views of the speakers and organizations participating in this webinar are their own and do not necessarily reflect those of Civil and Structural Engineer Media or its publisher, Zweig Group. If you have any technical difficulties while viewing this webinar, please submit questions or a brief explanation of your technical problem using the question tab on the GoToWebinar control panel, and a representative will assist you. During the webinar, you can also submit questions to our speakers using the same question tab. Submit your questions at any time, and we will try to answer as many as we can later in the webinar. Zweig Group encourages group learning for our events. If you are viewing the live webinar with the group on one registered person's computer, that person must complete and submit the multiple viewer registration form in order for everyone to earn credit. Download the multiple viewer registration form from the Handouts tab on the control panel. Submission instructions are on the form. Viewers of archived webcasts must pass a quiz in order to download a certificate of completion. Gary Sider will begin our presentation.
I'm trying to get my screen to share. There we go. Sure I get the right one.
There we go.
All right, I think this is the right one to share. Welcome everybody. My name is Gary Sider. I'm the host for your presentation today. We'll have another gentleman, Kerry Hannon, join us as well. We'll go through some brief introductions, but before I do that, I would like to just kind of go over the purpose of this webinar, what we're going to talk about today. Key reasons why we use helical piles in these types of extreme events. We'll look a little bit of how we diversify our products. Hubble Power Systems is our parent company, and Chance is our brand for our helical piles. We'll talk about selecting the right type of helical piles and anchor systems. Then we'll get into some details about loss of shoreline solutions using helical anchors and piles and tiebacks. Beach armoring. We'll talk about the FEMA coastal construction guidelines in various flood zones. Then we'll get into some case histories related to Superstorm Sandy from the recent past and also other more recent storms. We'll get into some actual lateral load testing that's been conducted on some structures in beach environments, and then also some case histories about past hurricane, flood, and foundation repairs. So this is me. Been with the company now for over 30 years, working in various aspects with helical anchors and piles. I'm a registered engineer, current or former chairman of the Deep Foundations Institute for the Helical Piles and Tiebacks Committee. I've worked in various aspects of design, got some different projects in terms of patents that I've been able to achieve over the course of time. So we'll also let Kerry introduce himself, and I'll make sure I'm going to give Kerry the control there. So you now have control of the mouse if you need it.
Okay, yeah, thanks, Gary. I'm Kerry Hannon. I'm with Foundation Technologies. Foundation Technologies is the southeastern distributor for Chance Civil Construction Products. So we cover the southeastern United States. We're basically the customer service face for Chance in the southeast. I've been doing this for, in another month or so, it'll be 22 years that I've been doing helicals with Foundation Technologies and Chance. For 14 years before that, I was in the civil site business, so in all aspects of the construction industry. So I've been doing this for quite a long time. I guess I'm considered an old guy
now. All right, thanks, Kerry. So why do we use helical piles? Key reasons: limited air disruption. I'll go through some of these bullet points, not necessarily all of them. No spoils. Helical piles are a displacement pile method, which means that we're not digging and removing any materials if you're not overly familiar with helical piles. They're perfect and great. They're good suggestions or solutions where you have site restrictions, and that could be anything. Building lot sites underneath structures, like you see in the photograph. Quality control by measuring torque is a great attribute of helical anchors and piles. Relatively low cost. They can be loaded immediately, and we say they're scalable, simply meaning that, as you'll see coming up in the diversity aspects, they come in a wide variety of sizes and capacities. So we'll talk about that. Well, how do we diversify ourselves with respect to our products? This slide's it's a busy slide, but it kind of is shows you the relationship between helical pile products and torque capacity ratings. Torque is very important when it comes to helical piles because that's how they're installed. We screw them into the ground. Again, if you're not familiar with their method, they're much like a wood screw in terms of how they install into the ground. They advance one helical flight pitch opening per revolution, and it's very common to have multiple plate elements like you see on those photos on the side. A couple other things about that: the products that are marked yes in that AC 358 column. These products have been independently verified by third-party consultants, ICC evaluation services, to show that they do comply with the International Building Code provisions, both geotechnical and structural provisions. And so that's one of the things that we're pretty proud of, and we believe that it distinguishes our products because not too many manufacturers have evaluated this many different types. Notice that we go from 4,000 foot-pound ratings all the way up to 200,000 foot-pound ratings. These are the ones that are more, that say SS or our type square shaft, which are these here. The RS are these pipe shaft products. So we go from slender square shaft elements all the way up to 4, 5, 7, 9-inch diameter pipe shaft helical piles. Torque factors, this case of T value that we show you, is a relationship between the energy required to install a helical anchor or pile. And you'll notice that the square shafts have the highest case of T values, which is one of the reasons why you'll see them being used as much as possible when it comes to helical piles. So selecting the right products, mention the building code. We have, again, 7 different products that have been evaluated for new construction, foundation repair, and they have recently been evaluated for seismic design categories D, E, and F. So for lateral load conditions or situations, helical piles are continuing to expand their breadth and their use in various areas of the country and throughout the world. So here's kind of an example of the different pile types that we have evaluated. A couple of different square shafts, pipe shafts up to the 4.5-inch, and I mentioned that we've recently added the seismic design categories D, E, and F. And we do have the most evaluated products in the industry, at least in the North American industry or markets. Buy America or Buy America. And for those of you who are interested in this type, if made in the USA is important to you, Hubbell Power Systems is the right choice. We have systems in place to ensure that we're providing helical pile products that comply with several of these federal statutes that you see right here. Depending upon the nature of your project, these Buy America, we have experts in our staff that can determine the proper material sourcing to ensure that we're meeting these statutory requirements. So if you have a project that is related to that, just let us know and we can provide you or do the best we can to provide you with those types of materials. Okay, so diversity over with. Let's talk about a little bit, get into the flood discussions about coastal conditions, and Carrie's going to go ahead and kind of take over for a little bit. So go ahead, Carrie.
Okay, being that I work here in the southeastern United States, we obviously have a lot of coastline that takes the brunt of the majority of the tropical storms and hurricanes that make landfall in the U.S. So have a lot of experience, both before and after storms, things that work and don't work. basically we had major hurricanes in the mid 90s with Opal, Aaron and Opal in the 95. Then it's kind of quiet for 9 or 10 years. We had Ivan, Dennis, and Katrina in 04 and 05. 3 major storms that hit the Gulf Coast in the span of 2 years. Then kind of quiet, had the very, very large Category 5 storm that Michael that struck the Florida Gulf Coast in 18, and Sally last year. So being that we have that much experience, we've seen a lot of the damage that is caused by these storms, and have had, I guess, the fortune to have repaired some of that damage and then seen how it survived the a subsequent storm. So you'll see a lot of before and after pictures that we're, are kind of fortunate to have. So the primary thing, that one of the biggest difficult things about a storm is the shoreline loss, and so that's what we'll be dealing with a lot here in the next few minutes. Can you advance the slides, Gary? All right, so
Got it.
Manage shoreline loss. There's a couple of different methods here. So one is hardened armoring, where you're basically going to draw a line in the sand and try to protect losing any more shoreline from that point forward with a seawall or a bulkhead. And we'll talk about different types of those. Or you can put the beach back. You can put the shoreline back with nourishment by dredging or hauling sand and replacing the shoreline back. You're typically, dependent on a government entity, involved in that. Can involve a lot of time. A lot of the, in my opinion, the best solutions are a combination of 1 and 2, where you're going to harden it as well as do some beach nourishment, put it back. And then there's 3, managed retreat, which is loss of property. And not too many people that own shoreline property want to talk about number 3. So we'll mostly be dealing with number 1 and 2. So there are 3 types of seawalls and bulkheads that we'll talk about, or structures that you'll see on shoreline, trying to deal with shoreline, prevention of shoreline loss. One is sheet piles. It can be steel sheets, composite or vinyl sheets, wood sheets, wood lagging, different types of sheet piles. Next, also you have piling that to support an above ground structure, either to provide a blowout floor for a washout floor for flood waters to come underneath, or to support a structure above ground in the event of loss of soil and a scour event, like you see in the picture here. Or a gravity wall, which is basically blocks or baskets or socks filled with stone or soil or sand, and just the sheer weight of these structures hold the wall in place. So the type of damage that you see from hurricanes can be divided up into 4 categories. One is the wind damage, that's typically what you see on the news video feeds. It's usually very spectacular. Not so much what we're going to be dealing with today. If your roof blows off, it's you can put it back. But the other 3 are what the kind of damage that we're typically going to be dealing with the shoreline loss. And one is wave damage, where you've got structures that are not used to seeing wave action or water damage. They're getting beat on by waves that can cause an awful amount of damage that they're possibly not designed or built for. One of the larger damage events is the storm surge, which is basically a huge flood event where this big wall of water, sea levels rising, that's being pushed ahead of these low pressure centers, these storms that flood areas that can, storm surges can be in excess of 20 feet at times, and so cause massive flooding damage to all types of structures. Number 4 is when that storm surge ebbs or scours or goes back out to sea. And a lot of times the vast majority of the damage is caused by that. The storm surge typically comes in, you know, it depends on the storm and the geography and whatnot, but comes in over a period of several days, probably preceding the storm. And then once that low pressure system passes, there's nothing to hold the water up there anymore, and it usually recedes much, much faster than it came in. And that causes an awful lot of the damage that we see from hurricane events. So what type of wall do you need? What wall will work? Well, if you're football fans and as old as I am, you might remember Jerry Glanville, was a very colorful coach in the NFL, and he coined a phrase that was aimed at referees that making bad calls. That the NFL stood for not for long. That, you know, if they continue to make bad calls, that they wouldn't be in the league. They wouldn't have a job for very long. Same thing with a wall structure. If you know, you're deciding what to get built, if you make a bad decision, a bad call on what type of structure, it's in the southeastern United States, it's probably not going to be there very long. And we'll show you some examples of that. So after Hurricane Opal, there was a study that was done by the National Science Foundation, put together, that studied all the damage and the impact of Hurricane Opal on the Florida-Alabama coast. So a lot of this information came from that study. So it's based, you know, that they identified that the type of structures that we're going to talk about, how they did significant saving of structures, preventing damage, but many of these structures failed, and they tried to categorize and highlight the reason that some of these structures failed. So there's three main types of failure. The first type is end-around failures, erosive flanking. Basically, and it's a very common problem. I'll just go on to the next slide. I'll get into that a little bit later, because you have multiple property owners. A lot of times it's hard to prevent that flanking because you don't have a continuous wall. So here you can see this timber soldier pile, timber wall, timber sheets on the right side of this wall. You can see how it had a wing wall, it turned back into this condominium structure here on the right, and had very minor damage where it got slightly flanked, and they didn't lose a lot of damage, didn't lose their wall here on the right side. This was after hurricane, so this wall the dunes used to be up here near the top of the wall. That's how much shoreline or beach dune action was lost. And then the very next year, Dennis came, or this is after Dennis, this is after both storms. Go to the next slide. You'll see the left side of this wall, where the wall was not returned back all the way to the adjacent building, and see the kind of damage that came just by coming around the wall. The wall was tall enough and survived the storm surge, but it got flanked around the end, and they lost a huge amount of area, pool deck, and whatnot, patio. The other second type of failure that you see these type of structures have is a seaward toppling, where the wall basically gets overloaded by hydrostatic pressure. It has way more load than it was intended to carry, and it topples over towards the sea. So here you can see this wall. Again, the sand used to be up here and survived Ivan, you know, very intact looking structure, but it lost that much sand, you know, and in front of it. So the wall, when the next storm, when Dennis began, the wall was already much taller. Next slide. And you can see the same wall did not survive because it just didn't have enough. It just got overloaded because it didn't have. There was all that sand that was in front of it before was not there to get washed away during the first part of the storm. Next slide. So here's another view from the land side to see how it toppled over towards the sea. The third type of failure is scour, where you know the wall is undermined, you're losing toe and your wall's got enough amount of toe in under the ground, and then exposed height above ground. And by scour, you're increasing the exposed height and reducing the toe. So here you can see another timber wall that survived Ivan, and you can see here is the bottom of the lagging. So lost a good bit of toe here. Probably, it's like a couple of feet, maybe 3 feet of toe in front of that wall. And the very next year, they didn't get the beach put back in time. And the next slide, you'll see, and Dennis came through, increased scour, wall's gone. Just can't survive that kind of loading. So what is a good wall? What should your wall be designed for? Well, that's a difficult call to make exactly. If you have private property, you have to make some kind of educated decision. But Opal was considered a mid-level hurricane, a Category 3 hurricane, and it had a 12 to 16 foot storm surge at low tide. And so, again, a lot of the news that we see on the news media is, whether it's a Category 3 or 4 or 5, which is wind speed, which is the wind damage, but the rain events that they can generate. Just because it's not a high category storm doesn't mean that it's not a huge rain event, and that it can't have a very large storm surge that causes much damage. So you want to try to have your wall designed where it will not get overtopped over whatever a reasonable prediction of a storm surge might be. So here you can see it's an example of both the wall not being tall enough and flanking. So you can see these 4 homes got together after Ivan and built a gravity wall. These are socks that are filled with sand. And you see on the left side of the wall, it was returned back up underneath this structure, and it didn't get flanked here. But it got overtopped, and on the right side over here was not returned back far enough to the road, and so all the water that came over the top of the wall has to find a way out when the ebb scour phase comes in, and it ran out on this side and took all that sand with it. So an example of both overtopping and erosive flanking. So here your walls need to be turned in far enough back so that they have a high percentage of probability of not being flanked. You can see here, this was a new wall being installed. They ran into this wall that had been previously installed while this one was under construction. We've been much more efficient, to have a continuous wall there, but it's always difficult with different property owners, timing, money, etc. All right, so seaward toppling, overloading the wall by rain or washover. So you want to have your wall to be tall enough to minimize the chances of that happening. And if your wall is tall enough, it most likely needs to be tied back because you won't be able to cantilever a height that tall. So that's where the helical tieback anchors are a great solution. So your wall's got to be tall enough to allow for scour also. So because as this storm comes and scour removes some of your toe, the wall is going to get even taller. So you have to allow for that. So your basic design concept is you're going to have some type of a rigid wall face, either soldier piles and lagging or sheets, steel sheets. And because of excessive height or lack of toe, you need some tension help to help hold the wall up. What's important about your tieback, whether it be a helical anchor, that it be beyond this failure wedge, so that the whole wedge can't fall over. Helicals are end-bearing elements, so what's very important about the tieback is that it has enough capacity, whatever the load that's intended to have on it as the wall height reaches maximum, and that it's long enough. This last helical plate is stressing this soil that's behind the failure wedge, rather than this soil that's in front of the failure wedge, and then your screw basically is not long enough, and the whole wedge could, topple over towards the sea. So here's an example of a very nice looking timber wall. You can see where the soil, the sand used to be up here prior to Ivan. Ivan came, removed a bunch of that soil, made the wall taller. And then in the next slide, you'll see as Dennis came the very next year, the wall got even taller, got overloaded even more, and now the wall's not there anymore. So what is it a tieback? It can be a drag wall, it could be a pile, it can be a dead man, it could be a grouted tendon, it could be a helical anchor. But no matter what type of tieback it's got to be long enough. So it's got to be behind this failure wedge. So next slide, please. So here you can see there's just, after Ivan and Dennis, there's just miles and miles of this shoreline that needs to be protected to prevent further loss. We had nice aerial photographs from this study that was done. This is the Adagio condominiums on top of this bluff. This is the highest point on the Florida Gulf Coast at about 34-foot bluff. You'll see some more detailed pictures on that repair in a few minutes. So here you can see a little small vinyl wall. Not that there's anything wrong with vinyl sheets. They used little drag piles, little small 4-inch drag piles that were only like 4 feet long. Couldn't have much lateral capacity to begin with, on a cable that must be 6 feet long or 5 or 6 feet long. So it's just right behind the wall. So nowhere, the wall's just not even intended to survive a big storm. It's just a Band-Aid. So here, this is on the east coast of Florida after Hurricane Charlie. It's hard to believe, but they built shallow foundations in the sand dunes up until about the mid 80s in Florida. So the storm comes through, they're able to get on the beach with rubber tired equipment and install tiebacks underneath this structure where there's no room to put dead men or a drag wall in. This is the Adagio condominiums that you saw from the aerial photo a second ago. So this is the beginning of the repair. They're installing helical tiebacks in this sand dune here. The next slide, you'll see they install the sheets after the anchors are installed. Then the next slide, you'll see them connected, making a connection through the wall into a wale that you'll see on the next slide. And it's got a plate nutted off on the wale here, and then they bury it with sand and plant it with sea oats. So now your new dunes can be created here to provide additional protection, you know, the next storm event that comes through.
That's great stuff, Kerry. Appreciate it very much. A lot to look at and to consider when it comes to beach armory. So we're going to change gears a little bit. It's kind of the same theme. We're going to look at elevation of structures now and looking at some of the FEMA requirements, which I'm sure many of you are familiar with. Hopefully you've seen this document, the Coastal Construction Manual. For some of you have been dealing with this type of construction for years. It's a pretty useful reference. It gets into the basic recommendations for several of the FEMA flood zones. We'll talk briefly today about how helical piles can be used in these situations. And primarily, you would look at helical piles for elevation of structures like this when we're looking at situations that it's not possible to elevate the structure by moving it from the site or off to the side and then installing piling afterwards. If it's not possible to do that, helicals are a great choice. So we'll talk a little bit about those A zone and V zone requirements when it comes to the FEMA recommendations when it comes to flood zones. These are just a few of the FEMA manuals that are available for you. All you got to do is download them from their website. This FEMA P55 is the one I just showed you on the previous slide. The Coastal Construction Manual, a lot of really good information available in there regarding recommendations from FEMA. When we look at elevation of structures, we have to look at the pile in the sense of what we're trying to do as an element, a compression element. It's going to be resisting, obviously, axial compressive forces, perhaps some tension or uplift, and also, in some cases, considerable lateral forces. So we have to deal with unsupported length, and we also have to deal with soil types with respect to how deep or how embedded these piles have to be. in terms of achieving fixity. But we also have to look at scour as part of that, as you saw in several of those pictures that Carrie showed you, that scour is a significant event when it comes to the storm surge and flood. So we often have to, depending on locations, we have to look at scour in addition to this when we look at the overall pile length for a given location. So just some of you may be familiar with some of the FEMA zones, flood zones, and zone 5 or zone, I'm sorry, not zone, zone V zone, if you will. Quite often what the FEMA guidelines or requirements is that you have to have your lowest horizontal structural member, they call it the LHSM, that has to be above the BFE, as they refer to it, which is the base flood elevation location. That will depend on where you're located, what part of the coast. If you're in the Florida Gulf Coast, up the East Coast, in New Jersey, you know, wherever, Long Island, it will depend upon your location on that, on these various zones as well. The V zones, the A zones will also are suggested or laid out by FEMA, and then in some cases they have to make decisions on exactly what street and locations those come down to. But this is the general guideline for V zone requirements when it comes to elevation. So if you're going to be augmenting or adding on, you simply have to get your structures above that BFE is the main point. When it comes to V zones, it's interesting. FEMA recommends using what's referred to as an open foundation, which, as its name kind of implies, it's open underneath the structure. Reasons for that is what you kind of see in this picture. When you get debris flow, if you're having cross bracing, it's going to catch it, and that will obviously apply loads to your structure, which you probably don't want to have. So it's, you know, open foundations are intended to minimize the obstructions to storm surge and flow. These bracing may or not work very well. You can use false panels or low pressure panels as a way to provide some coverage that that looks better, and we'll talk a little bit more about that later. So we're looking at, you know, the pile types. Obviously, these are timber piles. In most situations, if you have an open site and you're building new construction, some type of timber pile is certainly an attractive option. There are others, but open sites and cost relationships, these types of piles are typically better in that from a cost standpoint, as most people would understand. When we're looking at support using grade beams, sometimes we're looking at footings or grade beams and using helical piles or micro piles as our way of connecting. It's a very similar concept of what you've seen before in terms of making sure we're above those base flood elevations. It's not uncommon to use some kind of a footing or grade beam. Have to obviously consider scour whenever you do that. So you can see different suggestions here. Battering helical piles for lateral support is also a good way to resist lateral forces. And we'll show you an example of that here shortly. Now, this leads up to the point that when you're looking at pile shaft design, you know, I showed you earlier that we have square shaft and pipe shaft helical piles. You know, if you're looking for lateral load resistance, obviously pipe shaft type products, or what we call our pull down grouted shaft piles, are very good for resisting lateral forces. It comes down to how much resistance you can develop with the stiffness of your shaft and how much passive resistance that particular diameter shaft will provide. Obviously, with a V zone open structure, you may need additional or more supports than you would for, say, for example, an A zone, which doesn't require as much elevation, and you're not having to worry as much about a storm surge in an A zone area. So types of helical pile solutions that I'm going to show you here are for structures that have to be just simply vertically raised and then the piles installed underneath them. In other words, there's no room to move the structure. And so how can you do that? Well, in some cases, people just extend a helical pile, and above grade extend a pipe shaft or a casing above grade in order to provide that support, not only for the axial loads, but also for the lateral forces. I mentioned earlier, grade beams, in some cases with tiebacks, are also an option that can be used. And then cross bracing. Again, you can use cross bracing in A zones and sometimes in B zones, just depending upon how it's done, in terms of and what direction of the, if you're more familiar with the direction of the flow will be, which isn't always easy to know that. So I'm going to go over one project that I think you'll find of interest. This was a project that from the past, from Superstorm Sandy. So hope some of you probably remember that event. Quite devastating, caused billions of dollars in damage, a lot of it right along the Jersey Shore, Connecticut, Long Island, you name it. And so helical piles are used, continue to be used in some of those areas for support or elevating structures in order to provide to accommodate with the FEMA flood zone requirements. So this project here's some of the individuals that were involved, the project engineers, the pile contractors, distributors. The thing that we're going to focus on is that we were able to do some full-scale lateral load tests on this structure, which I think you'll find of some interest here for this presentation. So here's the structure as we first came on it, in terms of our testing. It had been elevation contractor had lifted the structure, which is an art form in and of itself, as I'm sure some of you probably know. And so the contractor was going to start installing the helical piles underneath the structure as part of the support, overall elevation support of the structure. So here's an example of one of the attributes of helical piles. You're working directly under this elevated structure. You see this mini excavator rig. He's installing the helical pile right here. He happens to be directly under the chimney at this point, which is always interesting when you're standing there directly under chimneys of a structure. But that's the way this is done. So you can see some of the attributes of helicals in that respect is it's not going to be easy to drive piles with a pile driving rig with that type of situation. Ground conditions, I'm not sure how well you can see it. We had some overburdened sands and then some very soft peat, very smelly, nasty peat soils down to 10 to 15 feet, and it got into a medium dense to dense sand. And we were able to install the helical piles into those sand materials for this project. So the test piles for the lateral load test, we had 3 different types of piles. We basically had a cased pile, 6-inch casing, steel casing. We also had an 8-inch steel casing. These were Schedule 20 steel casings. We also used where we cased the lower portion of the pile extended down into the ground, but above grade we used a 10-inch PVC that we used grout and a fiber reinforced grout material to form the column. All of them connected to the structure at the top. Overall pile lengths were, as you see here, in the range of 22 to 23 feet. The tip elevations you can see here, about 20 feet, give or take. Some of them are a little longer. I'm sorry, these were more like 29 to 30 feet overall, going up to near the bottom of the structure. So we had about 9 to 10 feet of unsupported shaft length for these. So we tested these in pairs, and I'll show you some of the photographs. Here's some of the piles. This is the pile, the grouted shaft. We took the PVC casing off for the test. And you can see some of the ways that we were attaching the piles to, again, test them together in pairs. So we just followed standard ASTM methods for deep foundations under lateral loads. Kind of go through these details. We held the loads, applied the loads with a chain hoist, and we measured deflection at 2 places, both at the base of the exposed pile above grade and also up at the top near where it was connected to the cross beam that we used to connect them together. And I mentioned again that we did this in pairs. So you can see here kind of our connection at the top of our piles. So it's not, somewhat, you could say it was somewhat semi-fixed type connection. Here's where our dial indicators were located when we were yanking on it sideways. You can see our load cell here as we're pulling on it laterally. So it's kind of a busy graph, but it's kind of showing some of the results. The one that was able to load the highest was pile number 4, which had that 10-inch fiber reinforced grout column. We were able to put about 8,000 pounds of lateral on it. Deflection at the base is here. Deflection up at the top, about 9 feet above grade. You can see we went over 6 inches several times with several of these piles. So quite a bit of movement at the top. So, to kind of summarize some of this, the first piles 1 and 2, which had the 6-inch steel casings, we were, we basically were saying we had about 2,500 pounds of lateral allowable, which is about 1,300 pounds per pile. The better performing one, we had about 2,000 pounds per pile. What was that 10-inch grouted shaft? And then the 8-inch one, we didn't quite have as good a result, so we had a connection failure, which kind of adversely affected our results, which, that's real life. It happens obviously when you do tests. Allowable lateral was when we had about 1/2 of an inch, or half the load, we had about 1 inch of lateral deflection at the ground surface is how we define that. So what you're seeing here is kind of a plan view of the eventual structure. It's kind of hard to tell. Obviously, this is the vertical pile locations. This is where the chimney was or is. And here at some of these corners right here, you can kind of barely tell. There's these dotted lines. The pile engineer or the foundation engineer decided to put in some lateral anchors, battered anchors, in order to resist additional lateral forces, over and above what he used for the piling itself. Here's a detail of that battered anchor. It was another helical anchor, battered at about a 45-degree angle and connected at the top, as you see here. And here's an example of the piles underneath the structure with the casings that were used. And here's the connection detail at one of the corners. This is a decorative square fiberglass column that is, was used more for the aesthetics, ending up with this type of result for that structure. These are low pressure breakaway panels. So this is truly an open foundation, V-zone type, but it looks, obviously, it was a very nice result. So we're going to switch again to some different aspects of foundation repair. I'll cover a few in the time we have, and then Carrie will also cover a few as well. This is a fairly recent project, Hurricane Sally in Perdido Bay, and you can see what Carrie was talking about. This is a seawall failure. And you can see what's happened. It undermined the structure of this foundation. In some cases, quite a bit of undermining. The interesting part about this, the only way they could get the equipment to do the work was by a barge. They used helical piles to do a foundation repair for this project. So here's how they brought the equipment to the site. Here's another picture of it. There's your mini excavator getting ready to do the work. And here's giving credit to some of our folks here that did the work. Kerry and his company provided the materials, and Mason Grady was the foundation contractor. And then you can see the other engineers that were involved in terms of the general and the project engineer. So here's the rig installing the helical piles underneath the foundation. Here's a little bit better picture of it. They installed 2 7/8 pipe shaft helical piles, but they also encased them with a grouted casing in order to provide additional stiffness to this grout shaft or the column because of its unsupported length. And you can see that in this case is these unsupported lengths underneath these foundation repair brackets in order to make sure that they had enough pile stiffness for this repair. So kind of gone through that pretty quick, but that's one example of the use of these helical piles. And so now at this point, Carrie, we'll come back and give you some more examples from past storms.
All right, I'll try to go through these quickly and save a few minutes for questions at the end. If you don't have time to get your, please submit them and we'll get to you after the presentation. All right, this is a Captain Dave's restaurant in Destin, Florida on the Gulf Coast. It claims to be the oldest restaurant on the Florida Gulf Coast. And this is one of the structures that was damaged very heavily by Ivan in '04. A major portion of the restaurant was underpinned with helicals. New construction helical piles were put in for other portions of the restaurant that were damaged or that were basically unsalvageable, where they had to rebuild portions of the restaurant. And the very next year, Hurricane Dennis came through and took a really big hit to it. So here you can see that on the left, this foundation was underpinned after Ivan. And then here in the foreground, you see new construction piles that were used to pour this new slab, where a slab, they had to demolish the slab previously. So you can see how it survived. The structure was undermined here, but survived. Same thing here. This was underpinning was done. This is on the beach side after Ivan. And then this new deck was installed that you saw in the previous picture. They pushed sand back in here after the storm, seeing how quickly storms can reappear. But you can see how well the piles supported this wall in the storm event after it was undermined. A few more pictures. So here again, you can see the underpinning piles, new construction piles, where the new slab was poured. These are actually on the right picture on the right, these are slab brackets. So these were underpins of a slab that was deemed salvageable. So they cut holes, poured these slab brackets to underpin this slab. And then you can see how far it was undermined after Dennis. Again, this portion of the restaurant was underpinned and helical piles supported. This portion of the restaurant did not have piles and basically got washed out to sea. Here's a structure on the east coast of Florida, New Smyrna Beach, after Hurricane Charlie. This hotel was built in the 20s, a large mat foundation built right here on the edge of the water. You can see where the beach used to be, how much shoreline they had lost. This building didn't have a lot of structural damage to it, actually, but they were worried about it settling towards the water from the removal of all this overburden pressure. So they wanted to pile the water side of this structure to prevent that from happening. So here you can see how rapid response, rubber tracked equipment, how close to the water, piece of equipment that you can get in any rental market, any third world country, basically. This is the only special piece of equipment that you need. Driving 3.5-inch pipe helicals adjacent to this big mat to keep it from settling. So you can see they are attached. They had this big mat foundation to work with. So they're, instead of using underpinning brackets, they're attaching these piles with a concrete haunch. So this pile's been cut off, got a heavy plate attached to it. This pile will be done the same way. Then they will dowel into this mat, reinforce this thing, and pour it with concrete. And there's the line of piles on the water side of this hotel. This is at a remote island, Kewadeen Island in Southwest Florida. There's barge-only access. There's no bridge to it. So this is, home fish camp. It's been flooded by one of the storms. They bought a house mover in, jacked the house up, got it sitting on timber cribbing, and you can see the type of equipment that you can get, the headroom that you can get underneath these structures and place piles with. Then they would pour grade beams and come up with some type of a column. All right, this is a home in Pensacola, Florida, that we had before and after pictures of Ivan. So this home, they were doing a major addition renovation to it. So in order to get the permit to do the addition renovation, they had to make it pile supported. So in this picture on the left, you can see the underpinning piles were the existing structure they underpinned to make it pile supported. And then in the foreground, you can see some new construction piles where they were doing an addition here. So Ivan came through, the home was undermined. You see it's undermined about 18 inches, and this home was still standing. The home on both sides of this house had to be demolished, and they had to start from scratch. So you can see how the undermining here, the underpinning piles, but the structure survived. This is another house raising example, case history. This was here in Atlanta, Georgia. We had a major flood in '09. So this was a large 2-story house that used to sit on a concrete slab right here. So house was flooded, wanted to prevent that from happening again. The base flood elevation has been elevated over the years since the house has been built. So in order to get flood insurance, they need to be able to get the structure, the living area out of above the floodplain, the base flood. So it's got it sitting on timber cribbing, allowing you to get underneath and install high capacity piles. These are the grouted helical micropiles. So you can see the type of equipment that you can get underneath these structures with and installing the grouted helical piles. Then you pour your columns up, pour stem walls around the outside, and then put a nice brick skirt around your new blowout wall.
Yeah, just a nice cottage there.
Yeah, very expensive home in there in Atlanta.
Okay, excellent. Well, in the time we have left, we have a few minutes left. Just a couple of more things about the value proposition for Chance helical piles. The technical design manual, excellent reference, goes through a lot of the information that we've talked about today. Here's the actual location of that out on the Chance Foundation Solutions website. So you're certainly able to download that full technical manual. Good reference. Helicap software. Some of you may be registered users of this software. This is the landing page for the software, hbsapps.com/helicap. If you don't have an account, you can immediately create your own new account. Anybody can use it. It's very useful in design of helical anchors and piles that we've showed you today. Support. One of these days, if we actually come back together and do face-to-face seminars, we do have support. In addition to Kerry and his organization with Foundation Technologies, we also do quite a bit of work within our own staffing here, located in Centralia, Missouri. Training services, you name it, we can provide it for you. And again, just to kind of recap the experience, some of the tools that we offer you as well. We're the only manufacturer that we're aware of that offers this an online helical course, training and certification process. Kerry and his company, Foundation Technologies, is part of that in terms of training their certified installers. So we certainly appreciate this opportunity, and we're a little bit over our window of time, but not too bad. So at this point, I think we're ready to answer some questions. So looks like there's been a whole pile of questions, so I'm not sure which ones we can get to, but perhaps we can get to a few.
Thank you, Gary, and thank you, Kerry. For the next few minutes, today's speakers will respond to some of the questions submitted during the presentation. Please continue to submit questions using the questions tab on the control panel. We're going to get to as many of these questions as we can. First question, how tall should the storm wall be to prevent toppling and scour?
You want to try that one, Kerry?
I said, how big is your storm going to be? That's, FEMA sets guidelines, base flood elevations on coastlines, and that you'll need to design for. There'll be, and it depends on the zone that you're in, that you fall in. So your first course of business would be to get the correct FEMA maps and documents to determine where the base flood elevation is coastal construction line and that type of thing. Well, how much scour that they'll establish in V zones anyway, how much, where that scour elevation needs to be designed to.
And I'll just add to that, I would strongly encourage you to check with local jurisdictions. Determining the zones and base flood elevations can sometimes get to be political. So please check with your local jurisdictions as well.
Moving on to the second question. Where can I get a copy of FEMA P55 Coastal Construction Manual?
As far as I know, I would just Google, I go to FEMA. It's been a while since I've actually done it, but my remembrance is it's pretty easy. I think just go and Google FEMA Coastal Construction Manual. I'm pretty sure you'll be able to download it. They're all free and available to you as a U.S. taxpayer. Yeah.
Third question. When is diagonal bracing required for elevated structures?
That's a good question. It comes down to often the type of design in terms of the overall foundation. Like, for example, in the project that I showed, the project engineer decided he wanted to use lateral tiebacks to provide lateral capacity at the various corners. He left the structure primarily open, but he put lateral tiebacks because he wanted additional lateral load. So it comes down to determining how much lateral load due to the wind speeds. It comes down to the flow, the storm surge flows in terms of lateral load due to that. The height, in some cases, depending on where you're located, your base flood elevations are going to determine how high the structure has to be. So it gets to be, you have to work within the local practitioner in terms of whether or not using cross bracing is the right way. Cross bracing, from my perspective, you can use it in A zones. You got to be careful when you're in V zones for sure.
Awesome. Next question. Can you expand on the lateral load capacity of helical piles?
In terms of capacity, it comes down to size. So what you saw quite often in the foundation repair photographs that we showed you, the helical piles typically started out as a slender element, and then we use grout, and then we use casings. The reason for that is for two reasons: to provide lateral resistance with the cased diameters. 6 and 8 inch diameters is not uncommon, and that's because you got to not only provide it for that passive resistance, due to you're loading the projected area of the pile horizontally in order to provide that lateral resistance, but you also have to deal with the scour issues. So you're going to have to make your casings long enough and deep enough to resist. I mean, in terms of how much lateral load they each provide, it's going to be highly dependent. You saw in some of the examples we were showing you, you're not talking tremendous loads with an 8 inch or a 10 inch pile. You're getting 4,000 to 5,000 pounds based upon deflection. So they're not going to be huge numbers, but again, it comes down to sharing that overall lateral load with how many verticals that you have. Wood timber piles, they'll have a certain amount of lateral load resistance, again based on their diameter and their embedment depth. So it comes down to determining what that lateral resistance is in those soil conditions. So, and you'll get, obviously the bigger the diameter, the more lateral resistance you will get.
Awesome. And I think we have time for one more question. So, can helicals be installed in cobble material?
Kerry, you want to go for that one?
Yeah, it depends on the size of the cobbles. Cobbles, yes. A lot of that depends on the type of helical selected. The square shaft, the more slender the shaft is compared to the helical plate, the better chance it will have into either penetrating into something very hard or finding its way around rocks, cobbles, those types of things. So if you have a cobble environment, you'd want a square shaft helical or what we call a combination pile, where you have at least a square shaft lead section that where the helical plates are on. You can transition that to a pipe and or encase it into a grout column, but it's very dependent on the size of the columns. I like, Gary alluded to a wood screw analogy. I use that a lot. Helicals are very much like wood screws. I tell people wood screws will work in softwood. They'll work in hardwood. If you use the right screw, they'll work in knotty wood, which I would say cobbles are analogous to doing knots. And you might have to work at it a little harder and try, work, but it can, in a lot of cobble environments that can be used. Some they can't.
Thank you. Thank you, speakers. As we finish, please make sure to download your certificate of completion now from the handouts tab in the control panel. You will have to add your name to the certificate when downloaded. If you missed our note at the beginning and you are watching the live webinar with a group on one registered person's computer, please download the multiple viewer registration form, which is also under the handouts tab. We need this information in case you are audited, and we are contacted to verifying this continuing education activity. There will be screenshots of your control panel to help you navigate these handouts. Additionally, this webinar has been recorded and will be hosted on csengineeringmag.com/continuing-education. Thank you to everyone at Chance for this presentation. Thank you to everyone who joined us. This ends today's webcast.
Thank you, everybody. Appreciate it.
Yes.
Have a good day.
Thank you. Let us drop us an email if we can help you. Hello, anybody still there?
I'm still here.
So what are how are we handling all the questions? We staying on? Is that a separate deal, or are we trying to answer all the questions that were submitted?
That's a good
I've
one.
answered a few.
I
We're
don't know the answer.
still live, so everybody can still hear us. If you
Okay.
guys will, I'm leaving this up so everybody can get handouts. I'm
Oh,
gonna send you guys an email with all the follow-up questions, and if we want to email them separately, we can do that.
Okay.
Or we can answer those questions now if you guys would like. If people are still on, that we still got about 265 live with us.
Oh, okay.
I think it'd probably be easier if we answer them afterwards.
Perfect. Okay.
So we done here? So we just check out?
Yep.
Yeah,
I'm right now.
All right, Anna, thank you. We'll talk to you next week.
Thank you
Perfect.
very much.
Thanks so much.